So class, let us see restriction of rotation. So as I said, as has just been seen, polyethylene provides the best fundamental model for a mathematical and physical analysis of molecular flexibility. It is now appropriate to examine the ways in which the structure of other polymer molecules affects the fundamental flexibility of the simple polyethylene backbone. Most substituents and variations in structure will tend to restrict rotation of a simple polyethylene molecule. The structural factors which restrict rotation may be divided into those found in the main chain or backbone of the polymer molecule and those found on side chains attached to the main chain. So, what are we studying? Structural, which tend to restrict rotation of a simple polyethylene molecule. So, structural factors which restrict rotation are divided into two types. Number one, those found on the main chain, that is the backbone chain, and number two, that is found on the side chain attached to the main chain. First, we will see the main chain. Now, this main chain is subdivided into number of bonds an atom shares in the chain, and second, resonance. The main chain of a polymer molecule may contain two types of structural feature which affect its flexibility. So these are structural features which affect the flexibility of a molecule. As I said, number one, number of bonds an atom shares in the chain. Obviously, carbon or any other atom in the main chain of the polymer molecule must share at least two covalent bonds in order to form this chain. One this and another one this. So one carbon shares two covalent bonds to form this chain. It generally assumes that the atoms enjoy free rotation about such a single covalent bond. It is assumed. Okay. Double bonds. If two adjacent atoms share another pair of electrons to form a covalent bond, such as C double bond C, it is generally believed that such a double bond cannot rotate freely and therefore introduces point of stiffness in the main chain of polymer molecule. So double bond means point of stiffness. The effect on the flexibility of the entire molecule, however, depends on the interaction of C double bond C bond with adjacent structural features. Paradoxically, means contradictory statement, an individual double bond reduces the number of bonding direction on its carbon atom to 3 instead of 4. So what will happen if I introduce a double bond? Then there will be only a need of number of bonding to 3, 1, 2. So 3 bonds, because otherwise there are 4 bonds now in carbon. But because of this double bond there are only 3 bonds. So direction, number of bonding direction on its carbon atom to 3 instead of 4 because of double bond, reducing the conflict between adjacent single side groups even as small as hydrogen, and thus increasing freedom of rotation about the adjacent CC bonds in the main chain. Thus overall, as seen in the die-in rubber generally is to retain freedom of rotation, softness, flexibility and elasticity. So if you consider only this point in the main molecule, if you consider only the part which is having C double bond C, that will be a point of stiffness. But if you see the overall molecule, then the number of bonding of carbon, number of bonding direction on its carbon is reduced to 3 instead of 4. So the positive effect which happened is that the adjacent hydrogen are not there now. means they are far away. So flexibility is increased. So in the and freedom of rotation is also increased. That's why it is a paradox. Okay. So as seen in dyne monomer, generally it is to retain the freedom of rotation, softness, flexibility. So don't get confused. Double bond increases the restriction of rotation, but as a whole molecule, the freedom of rotation increases. So you have to be very clear with this concept. Now small rings. An atom may also share more than two bonds in forming the main chain. If it is part of a small ring structure, five-membered ring generally quite rigid, six-membered ring only slightly flexible. The stiffening effects of such rings in main chain are commonly seen in polyvinyl acetals, cellulosic polymers, and cyclohexane dimethyl terephthalate. These effects are most easily seen in glass transition temperature and melting points. Okay. So rigidity is very high in five-membered ring and the six-membered ring is slightly flexible, and these effects are mostly seen in TG and melting points. And examples of polyvinyl acetal cellulosic polymers cyclohexane dimethyl terephthalate. Now resonance. Resonance, as the name suggests, what does resonance mean? Linearity. When several conjugated, alternating double bonds and single bonds in a functional group are stabilized by resonance between them. Okay, linearity. When several conjugated alternating doubles and single bond in functional group are stabilized by resonance between them, so you can see there are alternating doubles and single bond. Okay, but they are all joined. Huh? That's why they are conjugated. Conjugated means joined. This improves flat planar structure upon such a functional group. This imposes a flat planar structure upon functional upon such a functional group, and this flat planar structure constitutes a significant reduction in rotation and flexibility, and a significant increase in stiffness of the body. So restriction of rotation is there because of this planarity. Resonance. Resonance in benzene ring produces a flat, rigid structure which raises both Tg and melting point. Typical commercial polymers include poly, para, xylene, and phenolic resins. Similarly, effects are observed when resonators stabilize unsaturated heterocyclic rings are incorporated into the main chain of polymer. When resonance stabilization and planarity extend beyond the ring structure to include adjacent functional group, the size of the rigid planar unit increases and the stiffening point effect becomes even greater. Polyethylene terephthalate is a typical another commercial polymer such as phenoxy, epoxy, polyphenylene oxide, polysulfone, polycarbonate, polyesters, diallyl alkyd, polyurethane, and melamine resin probably owe part of their rigidity to such extended resonance linearity. Still further, polycyclic structures or resonating in a single plane, such as diphenyl naphthyl groups, produce even extensive stiffening. So more resonance planarity, therefore material is more stiff, therefore restriction of rotation increases. Further yet, polyheterocyclic structures produce even greater flat planar areas of resonance stabilization and greater stiffening and temperature resistance. For example, in polyimides and polybenzimidazoles, the ultimate stiffening effects of such large resonating planar structure may be observed in the new heterocyclic ladder polymers, which contain a continuous resonance stabilized linearity throughout their entire polymer molecule. Now, side chain structure.